Good morning, everybody. Can you hear me? Can you hear me? Oh, sorry. I think many of you have problem. Maybe you don't have any microphone or headphone, right? So what should we do? Let me see how many people are there. 13. Let me see. Oh, you can hear me. Okay. Sorry. So I promised to cast my vote today, and I have not gone there yet. I will go there soon. I don't know how long it will take. So let me review our syllabus first, and then we will see what we can do today. Not one. Okay. Okay. So we see that we are almost at the end of this semester. We have just three more chapters left. So graph programming, so max flow, and today we will start, and then dynamic programming and PNP and NP completes 1 week. So that's three more topics. I think. Okay. Let me start our discussion today, and then I will give you the slide. I'll upload the slide, and I will finish it and review and finish it in our next lecture. So this is a simple topic. I think we will start. So if we go to book, so book has chapter 26. It says maximum flow algorithm, and maximum flow, and like max flow networks, and mainly we need to cover here Ford-Fulkerson method algorithm. This is pretty simple algorithm. There are two algorithms actually, Ford-Fulkerson and then Edmond-Scarp algorithm. So we can cover only, we can skip this one. So I got some slides from PowerPoint information from online and compiled them, and I made my own slides. So let us start from here. Okay, so maximum flow as the term it says that it is a useful process. For instance, in our real life there are so many max flow applications. For instance, how fluid like petroleum fluid petroleum or gasoline fluid pass through pipelines, and the current electricity flow, electric circuits or electric line, traffic on road, and then data flow in computer network, money flow in economy, and such kind of application we are familiar with, right? So in real life, for instance, if there is a pipeline, what is that called? If there is a pipe and then some fluid like gasoline or petroleum pass through the pipe from one place to another place, right? So how the fluid passes in the pipeline. So as long as its capacity, maximum capacity, it can pass, right? And so at some point, if there is a bottleneck, or some point, if there is what is called a like big a gas station or pipeline station, in that at that point fluids are taken away, so it decreases. Okay, so that one thing is that the capacity, a flow cannot surplus its capacity at any point, right? So let us give us some example. For instance, over here, like this is a network graph, for instance. Okay, so it can be bandwidth or it can be flow. It can be fluid flow or something. Okay, so here these two means here it has capacity maximum 2 unit. From this is source and is the destination. Okay, and source, and A through A and B. Okay, so from source S to T, some fluids or anything passes. How does it pass? So it has from S to A, capacity is 2 unit maximum. From A to B, capacity A to T, capacity is 4 unit, right? So here there is more capacity or more bandwidth over here, but here there is a low capacity or low bandwidth. So from S to A, it can pass only maximum 2 unit. Okay, so although from A to T has capacity 4 unit, but it cannot, in case it does not find enough items or fluid to A, then it cannot pass through this path, right? Okay, so the maximum is to A, capacities, maybe fluid capacity is 2 units, so it can pass only 2 units from this here. Okay, maximum 2 unit, or you can give 1 unit over here, and you see that there is an arrow over here, so A to B has 1 unit. Okay, so if you pass 2 unit from over here, so then you can give 2 unit, both 2 unit over here from S to A to T, or you can pass 1 unit from S to A, sorry, 1 unit, 2 units from S to A, and then 1 unit from A to T, and another unit from A to B. Then 2 unit. Okay, and then from B to T, it takes 3 units maximum. So whatever it receives, so 3 units it can pass. If we pass, it has 5 unit capacity, and it has 3 unit capacity. Okay, so that we know, we in general we understand that it can maximum pass. It can maximum pass 3 units. So then what will happen if it gets more than 3 units? For instance, 4 unit or 5 unit, or it can get maximum, you see that 6 units, right? 5 plus what, 6 units, then what will happen? Okay, the general rule of thumb is that you can, whatever a node consumes or receives, it must deliver the same unit. Okay, so in any point, if a unit A receives 1 unit, it will pass that unit to here, to anyone. It will pass. It cannot hold, like electricity. Okay, so these transition paths are dynamic, so it cannot hold anything, even like electricity or fluid. Whatever it receives, it will pass. Okay, so that means B cannot receive more than 3 units. Okay, and from this situation, what A can receive maximum? we see that A can pass 1 plus 4, 5 units, but it can receive only 1, 2 units. So maximum it can receive 2 units and it can pass, so 2 units. Whatever it receives, it can pass, it pass entire thing. So it cannot hold anything. It cannot pass anything more than it receives. So here, yeah, don't be confused that from A and B. So A can receive maximum 2 units, but it can pass, although it can pass 5 units. Okay. So ultimately, we can say that although it can pass 5 units, ultimately A will pass maximum 2 units because A receives only 2 units. Similarly, although B can receive 6 units, but since B can pass only 3 units, so B will receive maximum 3 units. You understand? So B cannot receive, for this flow, B cannot receive and pass more than 3 units. Okay. The rule is that whatever a node or a point receives, it will deliver the entire thing. There will be no residual any path. Yeah. So in flow algorithms, flow charts, there are some constraints. Constraints means the conditions or the formulas. For instance, here, one thing is that, for instance, here, okay, so the constraints are from S to A. If S to A is 1 unit, then A to S is -1. Okay. A, the flow S to A is 1 unit, then the flow of A to S, the reverse flow, is negative number, the same. Okay. And then similarly, A to B is 1 unit, then B to E will be, A will be -1 unit. Okay. And so here, so we see that this path, it can pass only 1 unit, right? So then it has capacity to pass 2 units. So if it takes 1 unit for the path A to B, so then 1, we said this is bar, vertical bar means the capacity is 2, but you're passing 1 unit. So here the capacity is 1 unit and you're passing 1 unit. So this is consumed, right? And then it has capacity 3 units, then you're passing through 1 unit. So then the capacity of S to A was 2 unit, and then I took 1 unit. So then what is another 1 unit is remaining, right? So that means, so S to A has another 1 unit. Okay, then in the reverse order, we can say if S to A is 1 unit, then flow of A to S will be -1 unit. Okay. And if flow A to B is 1 unit, then flow B to A will be -1 unit. And if flow B to T is 1 unit, then flow T to B will be -1 unit. Okay. So the capacity is the flow for any two nodes U and B, flow of U and B is less or equal to capacity of U and B. So that means we said that the flow cannot pass its capacity, right? It may be less than or maximum equal. Okay, and this is the symmetric law. If flow of U to B is 1 unit, then flow of V to U will be 1 unit, that negative 1 unit. That means flow of U to V equal to negative flow of V to U. And the conservation is that for all U belongs to V minus ST. Okay, ST V, that means set of vertices, and S and T, S is the source and T is the terminal point. Okay, and then that means the remaining source for the all other except all other nodes except source and destination. Okay, the total flow will be sum of U plus V. That means from here to here, here to here, here to here, here to here, here to here. Okay, the total flow. Okay, that is the total flow we are counting. So the maximum flow algorithm, it assumes that a source produces the material at a steady rate and sink, that means T, sink is T or consumes the material at a steady rate. What that means, whatever rate it will produce at sink, it will consume that rate. Okay, that means both of them will be steady rate. That means they, whatever at any point, whatever they receive, they will pass this. So then we need to find what is the maximum net flow from S to T. How much we can pass from S to T. For instance, let us see a simple example from here. From A to S to A, capacity is 2 units. From S to B, capacity is 5 units. From A to B, capacity is 1 unit. From A to T, capacity is 4 units. And from B to T, capacity is 3 units. And these are straightforward. Now, let us write the flow constant. Flow constants are over here. From S to A, if 1 unit, we can pass if S to A is 1 unit. Okay, and then f of A to S will be negative 1 unit. As we said that, so this one is for the symmetric rule. With the symmetric rule, flow of U to V equal to flow of U to V equal to negative flow of V to U. And if we pass from A to B 1 unit, and then that will be flow of B to A will be negative 1 unit. Okay. And then flow of B to T, if we pass 1 unit, then flow of T to B will be negative 1 unit. So there is a term, it's called residual capacity. Residual capacity, for instance, given a flow F in a network G, that means graph-based network F of V, comma E, consider a pair of vertices U, V belongs to V for any two vertices, okay? Residual capacity is the amount of additional flow we can push directly from U to V. So it says the main word over here can. Okay, residual capacity is the amount of additional flow we can push directly from U to additional flow. Okay, we can push directly from U to B. So the main words, keywords over here, additional flow, and then it can be pushed. Okay, so if C of flow, okay, of U and V equal to C of U cost of U to V minus flow of U to V. So here residual C of F is called residual flow, residual capacity. Okay. So here residual capacity is equal to total capacity minus flow. You can remember that, and it will be always positive. Okay, capacity minus flow equal to residual capacity. So we will remember this term, capacity minus flow for any two node. Okay. And the residual network is formed with, is called G of F. Residual network is V of it's a set of vertices, comma E of E. E of E means the edges that are related to residual, that participate in residual capacity, is in residual flow. Okay, for example, if the capacity from U to V is 5 unit and then currently flowing is 5, sorry, if U of V is 16 unit, okay, and then if current flow is 5 unit, then residual flow will be 16 minus 5 equal to 11 unit. So you can draw something like this from U to B. Okay, the capacity is 16 unit and flow we are taking 5 unit. Okay, so that means C of flow will be 16 minus 5, 11 unit. And one thing is, remember that capacity will be, the residual capacity will be always written in positive number. Okay, let us see a few other examples. So here it was given an original graph. This original graph, the previous graph, with capacity 2 unit, 1 unit, 4 unit, 5 unit, and 3 unit. Okay. So here, so this middle one, it can pass only 1 unit. So if you pass 1 unit from over here, actually we need to start from S. So S to E to B to T, what is the minimum capacity that will be ensured? 1 unit, right? So even it can pass 2 units, it cannot pass more than 1 unit. And if you take only this path, then you will get only 1 unit from here at B, and then you will pass that unit from B to T, and then so here is 1 unit out of 3 passing, and here it's passing 1 unit out of 2 units. So here 1 unit is remaining, here 0 unit is remaining, and here 2 units are remaining, right? So the residual capacity for this path will be 0, here will be 1, and here will be 2. And if we do not use this path, what will happen? Okay, from this path and this path, if we never trust this path, what will happen? We'll come back soon. Okay, now here, so 1 unit, okay, there's a 2 units, so we passed 1 unit, so we have remaining 1 unit, right? So that means, so this is the, where did you go? okay. So here the residual graph is that it is not used, so it's 5 units remaining, 4 unit, this path is not used, 4 unit is remaining, and here there's one capacity was 2 unit, but we pass 1 unit and 1 unit is remaining. Okay, so then there's the reverse path, reverse order is said, and then 1 over here, and then there are 3 unit, and then we are passing 1 unit over here. Okay, then 2 units are remaining. So from here, let me show you. Remember that the symmetry property was something like if of no f of u to v equal to negative of v to u, right? So this is symmetry. Okay. So symmetry property is f of u to v equal to v to u, right? Negative v to u. So here that means this is negative. Original path was from S to A. Delete this. Okay. So original path was from S to A only. So S to A was capacity of 2 unit, and then we are passing to the one unit. 1 unit is remaining, and the negative 1 unit over here. This is negative 1 unit. That means it can take more. It can take more. Okay, and then how more it can take? 2 minus 1. You had capacity for 2 unit, you passed 1 unit, so then 2 minus 1 will be 1. 2 minus 1 is equal to 1. And then here similarly it had capacity 3 unit, it passed 1 unit. Okay, and then so it has capacity 3 minus 1, that means 2 unit. Okay. Okay, so this is called residual graph. I think there's a mistake over here. It did not show the path. It should be 1 unit. I'm sorry. I missed the deleted that one. Okay. So this one is a residual graph with flow augmenting path. Okay, so this one residual graph original, the black one, and then the new blue path is the augmented line. Okay. Now, what is about there? So here it says we has capacity 2 unit, right? And then we use this path for 1 unit. Okay, and then we have 1 unit remaining, right? So then what we can do, we can pass another 1 unit through this path. So here, as you can then you will say we'll take 2 out of 2 unit, and then we'll pass 1 unit here, and then I'll pass another unit over here. So then its capacity will be 4 minus 1, 3 remaining, and it has 3 minus 1, and it has 5, and it has 2 minus 2 will be 0. So it will have 0. This path will have 0 residual. This path have 0. This path have 3 minus 1, 2, and this path will have 4 minus 1, 3, and this path have 5. It did not touch. Yeah. Okay, so these are the example. Please go through this example and try to understand. Okay, so in if you don't, there are some examples. Okay, if you don't understand this, then we will discuss this in our next lecture. Okay, and then what in our next lecture we will go through Ford-Fulkerson algorithm. So the Ford-Fulkerson algorithm is straightforward. You start with a zero flow, and then it repeats until convergence. Convergence means until it uses maximum capacity for a flow. Okay, and finds an augmenting path from S to T along with along which we can push more flow. That means continuously it will be pushing more and more flow, okay, and augment flow along with this path. So this is the very straightforward in a way Fulkerson for Ford-Fulkerson algorithm. But so this is a little bit demonstration, and you see that in the later we see that demonstration is over here, and you see that algorithm is a little bit it looks me a little bit complicated. Okay, is here. Okay, this is the algorithm. Sorry, I'm at home. You can see noise. Okay. Okay, so this is the algorithm. Please go through this, and in our next lecture we will discuss this. Okay, so later better what I want to do, I can upload this slide in D12 so that you can read this slide. Okay, and then be prepared for the discussion in our next lecture. So in our next lecture we will give you some in-class activities. Okay, and let me upload this in here. This is the recent. Okay. Okay, it's added over here, and then let me add it in another section also. Okay. Okay, we have let me give me 2 more minutes, please. We are going to take the attendance today. Okay, before that, let me close my stop my recording.